So does anybody have any questions about homework problems? I could do a little bit of that before I start, but we have a quiz today, so I don't want to spend too much time on homework today. But anybody? Yep.
What are the expectations? Because we have the one rigid Freebody diagrams, and that all makes sense. But then the next one we're doing is like a big one, like 9 pages.
Oh.
Is that one? Are we supposed to be? Like,
No, you can't do that yet.
Okay. So
yeah, even the Freebody diagrams, I wasn't intending for you to start doing that yet, so you're ahead of. But with what we get through today, hopefully you'll be able to work on some of those, both of those two sets. Any other questions? Yep.
So what will the quiz be on today then?
All of the notes up through Thursday, not today, and homework problems up through particle statics. Okay? All right. Well, last time we did this. Did I start this? Yes. We did an example problem where we had a disk and a force F1 with an unknown direction and a force F2 with a known direction, where this angle was 30 degrees, and a couple. And I also specified the about point. And we said if this is in static equilibrium, so nothing's accelerating, what are the loads? So what are the vector F1 and the scalar F2? And we used Newton's second law and the rotational equation. This is a 2D problem. And in 2D problems, how many equations do you get from Newton's second law? 2. And how many equations do you get from the rotational equation? Just 1. In 2D, you only get 1 because any forces acting in the xy plane produce moments only about the z-axis. So you only get a z component here. And so we got, we had 3 variables, an x and y component of F1 and a scalar F2. We had 3 equations and we could solve for it. But this is not how rigid body problems appear when you're, trying to solve it in an engineering environment. We're one step away from doing like real statics rigid body problems, and that is that these unknown forces, the F1 and the F2, are not provided for you. You have to figure out what those unknown forces and other types of unknown loads are based on what kind of joints this body is attached to. So this leads into joints, which is going to be a big topic in this class. The problem above could originate from something like this, where you have a disk connected by a pin joint to the wall, and you have a couple applied at the bottom. Sometimes you have external couples that you know. any kind of external load that's given. And then over here, there's a pin on the disc that slides in a slot in the wall like that. And so this is like a real situation that would lead to the unknown loads that we had in that free body diagram. And then from there, we can solve for what those loads are. Yes?
Can you revisit coupling and its equal and opposite?
Yeah. Okay, so a couple for us is, like basically from now on, a couple is just always going to be given as a pure moment.
Okay, right.
And the way that moment comes about is you have a force going one way and a force going the other way. Like like if you're a receiver and you're really unlucky when you catch the ball, someone applies a big force to your chest and someone applies a big force to your feet, equal and opposite, and it creates a big moment. You know what I mean? And so that's a couple. And
Can you think of it as just like a z-axis?
it's a moment with a component in the z direction or negative z direction when you're doing 2D problems. Yeah, just like any other moment is. And it doesn't produce any force because the forces are equal and opposite, so they cancel each other. And what we saw is that surprisingly, when you're dealing with a couple, it doesn't matter what your about point is. So no matter where on this body we chose the about point, we would have this couple of negative 450 added to the moment equation, whereas the moments produced by this force or this force would change depending on what the about point is. Yep.
So a couple kind of, it would rotate the entire body no matter where the about point is?
That's right. I mean, it doesn't rotate it, but it tries to rotate it. Yes, exactly. You can think of it as like a screwdriver, like somebody just put a screwdriver, stuck it into the body there, and twisted it. It's trying to rotate the body. So the next step we have to take is we need to know what unknown loads are produced by each joint type. And we're going to do this first in 2D. We'll come back to it later in 3D. Okay, so joints. This is a big part of this class. A joint is a connection between bodies and each joint type applies a specific set of loads from one body to the other. What loads are applied depend on how the joint limits the degrees of freedom of the body. So what loads a joint applies to a body depends on how the joint limits the body's degrees of freedom. In 2D, a body has 3 degrees of freedom. It can translate along 2 axes and it can rotate about the z-axis. And here's how a joint limits those degrees of freedom. So a joint can only limit the motion of a body, compared to the body not being connected to anything, just floating in space. So first, let's think about translation. And think of the point on the body that's connected to the joint. If there's an axis along which the point can't move, when it's connected to the joint, then the joint applies a force along that axis to the body. The joint applies a force to the body along that axis. So let me show you an example of that. This is called a pin and slot joint. And imagine that so there's 2 pieces. This can zip along the slot. It can rotate like this, but it can't rotate out of plane. And it can't translate perpendicular to the slot. Okay. So think about the point, and we're just thinking about this in 2D. Think about the pin, the point on the rod that's connected to the joint. So think about the pin down here where my thumb and finger are right now, okay? Is there an axis along which the translation of the rod is prevented? Yeah, right. The way I'm holding it right now, it can't go up and down, right? It can go side to side. So there's no force applied by the joint side to side along the slot, but there is a force applied by the joint up and down that prevents it from moving. Okay, and it doesn't have to be a coordinate axis. It could be angled like this, and then that force is applied perpendicular to the slot, so this way, off at an angle. Okay. Any questions about that with the translation? So we're looking for axes along which the body cannot move at the point where it's connected. We're looking for axes where motion is limited. Yep.
So in the case of the pin joint, it would be perpendicular to the slot?
Yes, that's right.
Is it always perpendicular to the point?
It's always, well, in this kind of joint, it's always, every kind of joint will be different. But in something like this, there are other cases where it's, it's not too uncommon a thing because it's a normal force that prevents, like this is also a joint, this pin touching the table, And if you ignore friction, what's the axis along which translation is prevented? It just can't sink into the table, It can slide side to side. So that, so we'll have a lot of times where the force produced by the joint is perpendicular to a surface, yeah.
But it can be the other way. It can be different.
Yes, right. And then the other possibility is rotation. If rotation is prevented about the z-axis, no, this is all 2D still. We're not going to go to 3D for a couple weeks. So if rotation is prevented about the z-axis, then the joint applies a couple about the z-axis. And the big picture idea is that these reaction loads are what limit motion of the body. Okay, so I'm going to go through just a list of all the 2D joints that we're going to use. I'm going to put them into categories just based on how many variables are brought up by each joint. Anybody have any other questions before I go on from this? I guess I'm sort of picturing this being something you can go back to and try to make sense out of later. It's pretty wordy right now, but you can sort of think of this as definitions, where those reactions come from. Okay, so joint category 1. These are the joints that introduce one variable into the free body diagram. And they all do that by applying a single force in a known direction. So for all of these, I'm going to draw a picture of what the joint looks like, give the name, and then I'm going to draw free body diagrams of the two bodies that are being connected. So the first one is contact without friction. So you have one body like that, touching, like the floor there, and we're assuming that that's frictionless. I'll call the rod body 1, and I'll call the ground, what looks like the ground here, body 2. So part of a free body diagram of 1, the force that the ground applies to this body, we already know how to deal with that one. That's the first one that we ever dealt with. We know that the ground applies a pushing force, and so that force is going to be perpendicular to the surface of contact toward the chosen body. So that green line is supposed to be the ground, and so the force is perpendicular to the ground, and I'll call that R. And then if you draw the free body diagram of the second body, so like a chunk of this floor, that's body 1 is also applying a pushing force to body 2, so that force is perpendicular to this, and because of Newton's third law, that has that same variable value R. The second one in this category, so remember all of these that I'm numbering right now are the joints that introduce one variable. So the second one is the pin and slot joint. Let's see. So I'll call this body 1 and this body 2, and this is what I'm drawing. Okay, so the rod would be body 1, and the box would be body 2. This thing can slide freely, and it can rotate freely. The only thing that's prevented is motion perpendicular to the slot. A free body diagram of member 1. If the slot is this way, the force is perpendicular to it. So I'll call that R. And one important difference between the pin and slot and contact without friction is that, okay, notice R can be positive or negative. For contact without friction, this pen on the table, all the table can do is push up on the pen, right? But with the pin and slot joint, motion of this rod is prevented towards, I'll hold it like this. I can't pull the rod that direction, and I can't push the rod that direction. Okay, so contact with friction, or contact without friction, you can only have a positive value for that force. Pin and slot joint, you can have positive or negative. And which way you draw that vector is arbitrary. I could have drawn it the opposite direction too. Then free body diagram of body 2. Whichever way I chose this one has to be opposite because of Newton's third law. Any questions about that one? And then the last one in this category is a roller. Sometimes that's drawn as like a ball between the two bodies. And sometimes it's drawn with one of the bodies, it looks like we're sort of wearing a roller skate. But you treat it the same. So a free body diagram of body 1. Again, it's a force perpendicular to that surface. So if the surface is this way, then the force is perpendicular. And a free body diagram of the part of the ground, body 2. Newton's third law says it has to be equal and opposite. Yeah. There's no friction in this. So the only, so anytime in this class or any future class, anytime you see wheels like this, if it doesn't talk about the friction in the wheels specifically, that's meant to be like sort of a shorthand thing for saying it's frictionless.
So all in that place is going to be like positive, negative too? Or?
No, just, so yeah, let me, so why don't you go back up here and say, in this case, this is a pushing contact only, so somewhere just scrawl this in, R must be positive. And the same thing with the roller. R must be positive. The only one that's different is the pin and slot joint. I don't know why I did a question mark there. I think I meant to do an exclamation point. R can be positive or negative for the pin and slot joint. It can push or pull. Any other questions about that set of joints? All right, so now joint category 2. All of the joints in this category introduce two variables into the free body diagram. And all of these, the way that they introduce those two variables is by applying a force with an unknown direction. I don't think that door's locked. Okay, so that first category was all, the forces were all known directions. This time they're all unknown directions, so you have an x and a y component. The first one is a pin joint. It looks like that. I'll call the top one body 1 and the bottom one body 2. And that is this. Okay, so if you fix one of the bodies, what kind of motion is allowed by the other body? It's a little tight. It's supposed to allow it better than this, but we should have made the tolerances looser. But anyways, think about the point on, so body 1, the top one. Think about the point where it's connected to the joint. So think about the point that's like right at the pin. Can it translate in any direction? If this is fixed, can the point at the pin on this body translate in any direction? No. And so we know we're going to have an x and a y component of force applied. Can it rotate about the z-axis? It's supposed to be able to. It can a little bit. And so it's not going to apply a couple. You would only apply that couple if its rotational degree of freedom was limited, and it's not. Okay? So a free body diagram of body 1. Looks like this, and I'll call it the force on 1 by 2. And a free body diagram of body 2. The force applied to body 2 is the force on 2 by 1, and Newton's third law says that's equal to negative F12. Any questions about that one? And then the second type is contact with friction. We've dealt with this before. So it looks just the same as contact without friction, except that something says in the problem that there's friction. I'll call the rod body 1 and the ground body 2. So a free body diagram of 1. If this is the ground, the force is perpendicular to that. Oh, no, what am I doing? We already did that one. Okay, this is contact with friction, so we don't know the direction of the force. So we have an unknown force, the force on 1 by 2. And then if you do a free body diagram of the ground, here you have the force on 2 by 1, and that's equal to negative F12. Yes?
When you say that it introduces two variables in the full body diagram, are you
Yeah.
talking about the F21 and the F12?
No, I'm talking
F12, X and Y.
X and Y.
Okay.
So just because a single free body diagram would either be this one or this one, they would never appear in the same free body diagram. Any other questions about either of those? All right, and then the last one, joint category 3, only has one joint in it, but how many variables are introduced in joint category 3? Yeah, right. So the joint introduces 3 variables. And since there's only 3 degrees of freedom, there's only one possible way to introduce 3 variables. That is to limit 2 components of translation and to limit rotation about the z-axis. Okay, that's the only type of motion that's available to something in 2D. So it just says it doesn't allow any of it. And so this applies a full force vector, a force vector with an unknown direction, and a couple about the z-axis. Yep.
And by full force vector, you mean like you're in the X and Y?
Yeah,
direction?
that's right. Yep. So those are both variables. Okay, and there's only one joint of this type. It's a fixed joint. It just says there's no motion at all. You see it drawn like this. Sometimes people call it a weld joint. Sometimes you see it drawn with sort of a dovetail. But mathematically, these both mean the same thing. So I'll call the rod member 1 and the wall member 2. A free body diagram of member 1. Looks like this. You have the force on 1 by 2. And you have the couple M12. And then free body diagram of body 2. You have the force vector on 2 by 1, which is the same thing as negative F12. And you also have the couple M21, which is equal to negative M12. Any questions about that? Okay, let's just do a bunch of examples. First, let's say we have a beam connected to the ground by a pin joint. And then touching an angled wall there. This angle is 80 degrees. This angle is 60 degrees. And the length of the beam is 1/2 meter. And the beam has a mass of 100 kilograms. What are the external loads on the beam? Well, we're going to use Newton's laws. The first step is to draw a free body diagram. So here's an outline of the body. There's a weight force applied to the beam at the center that's equal to 100 times 9.81, so 981. And now we go around the boundary of the beam looking for contact. There's contact up here at the wall. What kind of contact is that? What kind of joint is that? Oh, well, I didn't say, so you don't know. Frictionless. Okay, so that's a frictionless contact. What do we know about that? What kind of load does that apply? Yeah, it's perpendicular to the wall, and it has to be toward the beam, away from the wall. So I'll draw this in at an angle like this, and then that force is perpendicular. I'll call that RW, our wall. Yep.
80 degrees on the wall, is that from the horizontal?
That's supposed to be horizontal. It doesn't look very horizontal. Okay, so we've dealt with that one. Now keep cruising around. You get to the bottom. That's the other place that there's contact with the outside world. What kind of joint is that? Pin joint. So what kind of loads are applied? Unknown force vector. Yep. So I'll just write that as the vector RP. One thing, so why did I use RP here instead of using force on the beam by the ground? That double subscript notation is useful when you have multiple bodies that you're going to end up isolating. It doesn't tend to be useful if one of those bodies is the ground, because you're not going to end up isolating the ground. So when something's connected to the ground, I tend to just call it R for reaction. If it's connected to another body, that's not the ground, I tend to call it F12 or FAB or whatever. Okay. Before we write out Newton's laws, let's think a little bit about what we have, if we have something solvable. Well, how many variables do we have? We have this scalar variable, and then this is a vector variable, so that's an x and y component. So we have 3 total variables. So we're going to need 3 equations to solve it. Are we, where we're going, are we going to have 3 equations? Yeah, Newton's laws give us 2 for Newton's second law, 1 for rotational equation. So this would be good. And now you see why this had to be a frictionless contact. What would have happened if there was friction between these two? We would have had 2 unknown components of force up here, because that's what a friction contact gives you. And so we would have had 4 unknowns, still just 3 equations, and we wouldn't have been able to solve it. There are more advanced ways to solve it that you learn about in D form, but for us right now, that would mean that we couldn't do this problem. All right, so now Newton's second law.
Question.
Yes?
Does it matter if on the wall it's a friction or frictionless contact if it's hinge joint on the opposite side? Since it can't translate, does it matter?
Yeah.
Friction or not?
So in this case, I think, yeah, you would, even if there was friction there, if you were trying to do this problem, like if you saw something like that on the street and you wanted to know what the forces were, you would, yeah, you would think to yourself, I guess, that because all it can do is rotate, there's no ability for it to slide up and down, so whether there's friction or not there, it's not going to come into it, and then you would treat it like a frictionless contact. And so you do have to make simplifications like that sometimes in real problems. Yeah, you're right. Okay, before we go to Newton's laws, actually, let's write out the pancake table. And I'm going to do it, I'm just going to do the shortened version, where I'm just going to do rho, and then force, and then the moment. We have to choose an about point, and you're usually best off choosing an about point to be where you have the most unknown forces. So let's make this the about point. And now we're just going to cycle through the forces one by one, calculate the vector going from the about point to the place where the force is applied, then put in the force vector and calculate the moment. So if this is the about point, what's the rho vector, the vector from A to the place where, to the pin? Yeah, that's a 0 vector. Any forces acting at the about point has 0 for the rho vector. The force vector is this unknown vector, so I'll call that RPX, RPY, and then 0Z because it's a planar problem. And if you take the cross product of 0 with this, you get 0 for the moment. Okay, next I'm going to do the, well, next I think I'll go all the way to the wall. So to calculate the rho vector that we want is from A to the point where the force is applied. How are you going to calculate that vector?
0.5 cosine sine of 60.
Yep, 0.5 times cosine and sine of 60. So that is 0.25, 0.4330. Now we need to come up with that force vector. How are we going to do that? for me, I think the way I would do that, if that's the coordinate system, I would first think of a vector that's parallel to this dotted line pointing up, because we know the angle from the horizontal to that is 80 degrees. And then I know that it's another 90 degrees counterclockwise to get from here to that RW vector. So we have 80 plus 90. That's cosine and sine of 170. And so cosine of 170 is like negative 0.985. Sine of 170 is 0.174. So then that's our force vector. And if you take that cross product, you get 0 for x and y, like you always will in 2D, and then 0.47 RW. Any questions about for this? 170. So this is RW times cosine of 170 and sine of 170. Okay, so I started at horizontal, and then I knew that a vector going this way is perpendicular to this, so I used the fact that it's 80 degrees to get from the horizontal up to that, and so I went plus 80 plus another 90 is 170. And now the last one that we have to deal with is the weight. This is a nice trick, a useful thing. This kind of thing is really useful in this class where you have to do a lot of trigonometry and stuff. If you ever need to find the components of a midpoint between 2 points that you know the coordinates of, just average the 2 points and it'll give you the midpoint. So you can think of this as like the average of 0, 0, and 0.25, 0.433. And so the coordinates, or the row vector where this weight is applied, is 0.125, 0.217, 0. The weight force is 0, negative 981, 0. And the cross product is 0, 0, negative 122.625. Yeah, and the last one? Well, I didn't use angles to do it. I just averaged. I imagined the origin being at A, and so the coordinates at A are 0. The coordinates here are 0.25, 0.433. Average those two to get the midpoint. But you also could say the length of like the vector you're trying to calculate is this. That has a length of 0.25 and an angle of 60. So you could do that as 0.25 times cosine and sine of 60. Get the same answer. Any other questions? All right, so now all we have to do, we've done the hard stuff. Now we just have to take these force values and put them in Newton's second law, and the moment values and put them in the rotational equation. So Newton's second law says, and I'm going to, when I write out Newton's second law, I'm going to ignore the z components because that is just going to be a 0 equals 0 equation. And when I write out the moment equation, I'm going to ignore the x and y components because those are just going to be 0 equations. So we have RPX, RPY, plus negative 0.985 RW, 0.174 RW, plus 0, negative 981 is equal to zeros. So that gives us our first two equations. The first one says RPX minus 0.985 RW is equal to 0. And the second one says RPY plus 0.174 RW is equal to positive 981. We can't solve those yet because there's three variables in there, but we will be able to after we do the rotational equation. And the rotational equation says 0.47 RW minus 122.625 is equal to 0. So that gives us our third equation. 0.47 RW is equal to positive 122.625. And so now you can, you have three equations and three variables. You can use reduced row echelon form to solve this. There's equation 1, equation 2, equation 3. And you can choose the order for your variables. I'll do it RPX, RPY, RW, and then these are the constants. So the first equation says RPXs, we have 1. RWs, we have negative 0.985. The other two are 0. Equation 2 says RPYs, we have 1. RWs, we have 0.174. Constants, we have 981. And everything else is 0. And then the third one says RWs, we have 0.47. Constants, we have 122.625. Those two are 0. Reduced row echelon form gives us the force vector RP is 256.99 and 935.6. Newtons. And then RW is 260.90. Yep.
And then for our RW vector, that's the magnitude of it, correct?
Yes.
Okay.
And so if you wanted to know what the force vector was that the wall applied to the beam, you would take that value and plug it back into this vector, and that would give you the force applied to the beam by the wall. But you can imagine how, if this was a real thing you were trying to set up, knowing what those forces were would be useful for figuring out how sturdy you had to make all of this stuff out. So we're kind of at the beginning of being able to figure out what we need to do so that the parts that we make these machines out of can withstand what they're being used for. All right, let's do the quiz.